In this video, I introduce a super resolution image generation via iterative diffusion refinement. Super resolution via repeated refinement is a cascaded conditional super resolution generation approach through iterative refinement based on denoising diffusion models and score matching. A conditional generation model P maps a source image X to a target image Y by adapting the noise and diffusion model to conditional image generation. For example, starting with the pure noise image YT as shown here. A denoising diffusion model iteratively refines the image through successive iterations from yt minus 1 to y0, as shown here. According to our learned conditional transition distributions pset, so that y0 is sampled from a conditional probability of y condition on x, as shown here. This is a forward diffusion process, and this is a reverse diffusion process. The forward diffusion process Q gradually adds Gaussian noise to a high-resolution image y0 over t iterations. If t is large enough, the final distribution yt of a Markov chain is close to a normal distribution. The forward diffusion process is defined as here. This conditional probability of y1 to yt condition on y0. This transition that is equal to normal distribution, this decay factor, and this variance of noise. Where alpha t determines the variance of the noise added at each iteration. Yt minus 1 is attenuated by a factor root alpha t to ensure that the variance of random variables remains bounded as t tends to infinity. Given y0, the distribution of yt is equal to marginal over intermediate steps as shown here, where gamma t is product of alpha I. The forward diffusion posterior distribution of yt minus 1 is computed by using this formulation for given yt and y0, where mu is mean and this is the variance. The posterior distribution is used as a reference in the reverse diffusion process to formulate a variational lower band on the negative log likelihood. The noisy target image y tilde is unknown and represented by E as shown here, where E sampled from a normal distribution, which is compatible with the marginal distribution of a noise image yt at different steps of the forward diffusion process. A denoising diffusion model alpha theta takes as input the source image X and the noisy target image Y tilde to recover the target image Y0. The objective function for training alpha theta is defined as denoising score matching as shown here, where X, Y is sampled from the training dataset and gamma sampled from distribution U is a schedule that determines the level of noise. The denoising diffusion model alpha theta is trained to match noise E over the training dataset. It's a method for training a denoising model alpha theta. Starting with the noise distribution yt, the reverse diffusion process is defined here. This is a joint probability distribution of y0 to yt condition X. This probability of yt and this transition. If the noise variance of forward process steps is small enough, namely alpha 1 to alpha t close to 1, the conditional reverse diffusion process p theta is approximated as Gaussian. The denoising diffusion process optimizes p theta close to the forward process posterior q. Given yt, y0 is approximated by y0 tilde as here. Substituting y0 tilde into the posterior q, the mean of p theta is written as here. The variance of p theta is set to be 1 minus alpha t. That is same as in the forward diffusion process. The update of iterative refinement is defined as here, where ET sampled from a normal distribution. This is a method for inference in T iterative refinement steps. This SR3 cascaded architecture is stage 1 and is stage 2. This iterative refinement process with unit structure. For more details, please check with these references. Thank you. Bye.